So let's move on and check the problem statement. If you direct an airflow onto a rotating disk with holes, a sound may be appeared. Explain this phenomenon and investigate how the sound characteristics depends on the relevant parameters. This slide shows us the setup that I used for this research. It consists of a tachometer, device that measure frequency of our disk, whole disk with holes printed with the help of 3D printer, microphone, a constant voltage source, motor, and an air supply device. So let's move on to the demonstration of the effect. As you can see, the sound changes as the distance between the geometrical center of disk and an air supply device changes. So let's try to explain this phenomenon. As the disk rotates, the air stream will pass when the stream and holes are coincide, and will be interrupted afterwards when the stream and hole are not coincide. Let's consider the case when they coincide. As the velocity increases, the pressure in the air jet decreases, and as a result become lower than the atmospheric pressure. For cases when the airflow and the hull don't coincide, pressure equalizes or almost equalizes to atmospheric pressure, and as there is no airflow. Uh, when the airflow and hull coincide, the pressure in the jet is less than atmospheric, then it equalizes or almost equalizes to atmospheric pressure. The resultant pressure oscillations causes alternating compression and discharge of air. In terms, alternating compression and discharge of air is an oscillation of the air. The fact is that a sound wave is an oscillation motion with small amplitude in a compressible gas with alternating compression and decompression at each point the sound appears. The number of holes in the disk and its rotational speed determines sound frequency. In the meantime, the greater the pressure difference, the greater the amplitude, and as a result, the volume of the sound will be greater. Uh, let's consider the passage of the air through the disk with trapezoidal holes. Let's draw a graph of dependence of driving force from time, and let's check each segment. When the air doesn't pass through the disk, the value of function will equal 0. Then it will increase when when the air will passes partially. Then when it fully passes through the disk, the value of function reaches its maximum, and then it decreases and equals to 0 when it not pass through the disk. Let's consider the geometrical parameters of our disk, which rotates with the angular velocity omega. Radius of disk we'll call r, and angle alpha we'll call Hall angle, while angle beta we'll call filling angle. Let's draw a trajectory. Uh, let's draw a trajectory along which the airflow passes. Next, let's show the position of the airflow under bordering positions. Let's consider these positions by numbers from 1 to 5 and make up a system of equations. The length of the arc trajectory on which the hull falls is considered by L sub alpha and can be found using this formula. The similar thing we could do for the similar thing we can do for the length of the arc along the trajectory which the hull doesn't fall. It will be called L sub beta, and also it could be used using this formula. Uh, so now let's consider a borderline position 2, 3. Uh, as the distance between the centers of the circles is 2r. As a tension. And the length of the arc trajectory connected these diameters will be found by this Formula. The time it takes for the airflow to travel from position 1 to position 5 can be found using this formula, where L is the length of the trajectory. Um, uh, let's obtain the final expression for the dependence of driving force from time. When the function increases, considering the coordinates of the first and last points, we can write a system of two equations for the line and find f from t function. Next, we can do the similar scene for the value of function between 2 sub 3 and 2 and between tau 3 and tau 4. And at the end, we can write down the value of the dependence of driving force from time for the whole interval from 0 to tau 5. Because our function is periodic, it can be represented as a Fourier series, where t is period, n harmonic number, and an intensity of the nth harmonic. Considering the fact that the an is the more general case of a0, we can write down these expressions and write down a formula for an for the value of an, where one of the factors of this expression could be represented as the sum of integrals from tau 1 to tau 4, to tau 2, from tau 2 to tau 3, and from tau 3 to tau 4. Integral between 0 and tau 1 and between tau 4 to tau 5 equals to 0 according to our graph. Frequency of the nth harmonic is a multiple of the base harmonic frequency is a multiple of the base harmonic frequency. So on the slide we can see two graphs. The first red graph is a graph of giant f from t function, and the second dark graph is a graph f from t function represented as a Fourier series with n terms. As we see, the greater the number of terms, the greater the convergence of the two graphs. Uh, let's consider the parameters of the problem we studied. Um, they are Among them are angle of Hall, filling angle, and angular speed of rotation. We recorded the sound with a microphone. Further, we proceeded the received recordings using special programs, and then got a spectrogram and an amplitude frequency response. As the sound wasn't clear, we proceeded to use a special program Audacity to remove as much noise as possible. Uh, in this graph, we observe the dependence of the frequency of the fundamental harmonic on the angular velocity of the disk. As the angular velocity of the disk increases, it passes the holes more frequently, resulting in the airflow behind the disk changing more frequently. The period decreases and the frequency increases. Thus, we observe good agreement with our theory. In this graph, we can observe the frequency dependence on the Hahn angle. In this experiment, we used three different disks, changing the Hall angle alpha, but not changing the fill angle beta. As we can see, as the angle alpha increases, the frequency of the sound decreases. In this case, changing the angle alpha increases the period, while the number of holes decreases. As the frequency is inversely proportional to the period, it falls as the angle alpha increases. This dependence has been received for several harmonics. A similar experiment uh, to the previous one was carried out with change in angle beta, with angle alpha unchanged. Similar to the previous case, as the filling angle increases, the period increases, and the number of holes on the disc decreases, resulting in a lower sound frequency. So let's move to conclusions. The causes of the sound have been described, what factors influence it, how it changes. These equations for the driving force is written down. The main parameters to be measured were explained. The methodology of the experiment was explained, the noise reduction was explained, the graph of the experiments were presented, frequency from angular velocity of rotation, frequency from field angle, and Hall angle. Thank you for your attention.